So, let's begin. So you should, no, you don't have anything to check, do you?
We should not do this.
Okay, so we are going to today, this is, like I said, this is the easiest, the last of the easy parts. I have a little hand in here if you want to try it. Do you want to come get the sheets out? Come for a walk? No, well, sort of. I'll do a test. Okay, let's begin. So this is super easy. So we're looking at force versus time graphs. This is from page 283 in the textbook. You've probably all stopped bringing textbooks to class.
Yeah.
No problem. Determine you are to determine the impulse in the area under a force time graph. Include constant positive and negative force and uniformly changing force. Okay, so let's go. So if a constant force acts over a time, hey. Yeah, absolutely, yeah. Okay, so if you've got a constant force acting over a time, the basic graph's going to look like this, right? Like, if you've got a constant force of, say, like, I don't know, maybe 15 newtons, it's just going to be flat line. The value is going to be 15 newtons over a certain period of time, right? And so what would be the area of that? Well, that would be the height times the length. That would be the force multiplied by the time, right? Well, force multiplied by time is the area under the graph, and we know that impulse is defined as the force multiplied by the time. That was the letter J yesterday, right? This is nowhere. You guys can write this if you want, or just sit back and listen. The impulse is force multiplied by, I guess we called it delta T yesterday, right? Okay, so therefore the area under the graph is defined as the impulse. So if you're finding the impulse and you have a graph, it's the, now when I say area under the graph, what if the graph is below? The area above, right? It's the area between the graph and the axis, right? Remember, we've done this many times. We've just had, now we're just putting different things on our x and y axis. That's all we're doing, right? Okay, so it's called impulse. Now, in most cases, the force is not constant, and it increases as colliding objects are compressed and decreases as they move away from each other, right? So if you think about like a golf club or a hockey stick, right, or tennis racket, if a tennis racket hits a ball, what happens to the ball? Compresses and then rebounds, right? So the force actually changes. Very rarely is the force in real life, Johnny and Dawson, very rarely is the force just flat. Quite often it's in fact, it increases and then it decreases. Well, now we've got a triangle. Can you find the area of a triangle? Yeah, you've been doing it since grade 6. Right? Now you should have this graph, I think, right? Okay, so again, the area under the graph is equal to the impulse. So in this case, the area would be what? It'd be 1/2 the base times the height. Right? So that would be 1/2 the base here is from 0 to, it looks like, 1.2. And the height is up to, looks like 25. So 1.2 times 25 would be 30. Half of that, I think, is it 15? Can somebody check my math with a calculator? Oh, 30, yeah, 15. I think, right? Can someone check that?
Yeah.
15. What's the unit again? Now this is actually impulse, so area. No, it's not newtons per, it's Newton seconds. Newton seconds, right? The area is equal to the impulse. J is the letter for impulse. How about we do this? How about I say area A equals J? Or J equals A, right? Okay? Good? Okay, so it says example 4. I don't know why it says example 4. It's probably in a larger section in the textbook, but here's one here. Here we have a stretched elastic band, applies more force than an Olympic elastic band. the applied force is decreasing over time as the stretch band returns to its relaxed state. So as you stretch it out, right, and apply the force, but then as it kind of comes back together, it applies less and less force. So here you will notice actually that it's not really a rectangle, it's not really a triangle. What is it? Well, it is a line, you're right. But then it's the area down, right? So it's a rectangle and a triangle. And we did this in grade 11 too, right? Yeah. Yeah. So the area here or the impulse would be, let's do it all in one step. Let's do that. Let's go 1/2 base times height plus length times width. You want to do it like that? So 1/2 the base is from 0 to 1, it looks like. And now the height of the oh, hang on. Yeah, no. Base is, to 1, and then the height now, the height is from 20 to 70, so that would be 50, right? Right? The height of the triangle would be from 20 up to 70, right? 50? Is that not the same thing? Okay, now the area of the triangle is going to be 1 times 20. So 1/2 of 1 times 50, well 1 times 50 is 50, half of that is 25. 1 times 20 is 20, so you should get 45 Newton seconds.
So that's all we're doing?
Okay, now, this is non-uniform changing. Now, if you go back to sort of the outcome, it was include constant positive and negative force, uniformly changing force. Uniformly changing means that the line is straight. Now, 9 times out of 10 in real life, it's not going to be uniformly, it's going to be non-uniform. It's going to be curved. Now, that's actually a bell curve, right? This is not required. I'm not testing you on this. I'm just offering you a little bit of enrichment for next year. How would you do that? How would you find the area of the curve? Yeah, you'd have to estimate, and then you'd also have to zoom in, right? And this is anyone plan on taking calculus next year? Maybe a few? Okay, so you'll learn about this. They'll have you zoom in here, and they'll do mini little areas there, and they'll talk about the limits, and they'll make some estimations and approximations, and you'll go, oh yeah, I remember Mr. Bennett kind of talking about that. You'll think back finally to those good easy days of grade 12 physics and how much easy life was. Can be solved by estimation or counting or calculus, and you would call that integration. Who's taking advanced math next semester? Okay, so Mr. Ray will be talking about integration as well. And you'll have fancy, you'll have this sign here. That's the integration sign. It's basically a elongated S for some of the areas, I think is what it means. If he asks you what that symbol is, tell him it's an elongated S, because that's what it is. He'll think you're really smart.
Yeah,
it is. That's what I've
so what you tell them. It's exactly what it looks like.
So here's an assignment. Now it's page 287, 6A and B. Now what I think I did was because I knew that students would write in the book. So what I did was I copied the book for you. So you can do it right on paper. Is that smart? Pretty smart, eh? That's pretty smart. Pretty smart. So it's right there. You can do some of those. Now, I have an impulse hand-in as well that's super crazy easy. Okay? And I also had students one time years ago say to me, Mr. Bennett, I suck at multiple choice. Can you give me more multiple choice questions to practice? And I said, And then I found some. So here they are. Here are 25. 25 multiple choice questions. Now I have the answer key to this. I haven't linked it. How would you like me to do that? Would you want me just to post it on Schoology? Is that the simplest?
Yeah.
Okay, I will do that.
This would have been beneficial at the beginning of the year.
Well, all I have is for momentum. Yeah, I know. Okay, so that's all I got. Tomorrow I will do 1D collisions. You did? Enjoy. Enjoy the next bit, too.